Okay, hello everyone, good morning ladies and gentlemen. How are you doing? Reasonably well? Good? Okay, so today we're going to study electrostatics in matter. This is a kind of 19th century type of topic. It's real physics. We have matter. For example, water. Water is an important matter. Inside water we have molecules. These molecules have dipoles. A lot of dipoles together create macroscopic effects. And these macroscopic effects have electrostatic effects. And these are the topic of the lesson today. That is, what is the relation between many dipoles together? They create something called the polarization field. And how does that give you an electric field? So imagine a medium. Inside there are many dipoles. You want to know what is the field outside. In some sense, in this lesson, the dipoles are going to replace the charges that we are used to. So instead of thinking about charges as creating some effect of fields, we are thinking about dipoles that are creating effective field. And this is a very natural thing. I mentioned water already, the most important liquid on earth, obviously. The reason is very simple. Most material, let's say this table, is not charged in the sense that the total charge here is not is zero. There are positive charges, there are negative charges, but many molecules, many atoms under certain conditions have dipoles. So there are many systems with our net charge zero and many dipoles inside, and then it's very natural to ask what are the effects. Now the lesson will be mainly on the macroscopics, but we need a microscopic picture of what is a dipole. Okay, so I assume you know what is a dipole. You have a positive charge, you have a negative charge. That's the simplest way to look at a dipole. The positive charge and the negative charge, if we look far away, what will happen? Will we have any Coulomb field? The answer is no, because far away these two charges, so there's a typical distance here between the two charges, and we are looking, at a distance much bigger far away, so the total charge is zero, so the Coulomb field is zero. 1 over r is gone. Then what do? We do something called, you know what it is, I hope, I'm reminding you, multiple expansion. It's called the multiple expansion, where we have two distances. What are the two distances? One is the distance between these two charges, let's call it A or D. And one is where we are looking at, we are far away. And we are assuming that this distance D is much shorter than where we are. We are not in, let's say, if we are two charges and I'm smacking her in the middle, then obviously if they are identical charges, then there will be no electric field in the middle. That's trivial, but I'm not looking inside the molecule, if you think about this as a molecule. I'm looking far away. And then the leading order expansion of the potential and later the field will be zero in the sense that there's no Coulomb field, but then there is a correction and the potential goes like 1 over r to the power 2. Because the Coulomb would be 1 to the power r, the distance, and that is vanishing because the total charge is 0, and then the next correction term is 1 to the r to the power 2. So this dipole, you can think about it as a kind of a weird charge that gives you, instead of the Coulomb field, it gives you a potential that goes like 1 over r to the power 2. Now there are more things like quadrupoles, but we are just going to do the first correction. Just look at the dipoles and forget about the quadrupoles. So let me remind you how this is done, and this, I think you know this. So in generality, what we have is, what we think about is a reference frame, and here we have some object. This object has an element inside. This element is a square element. It's an element of volume, and that is d tau. What is this amoeba that I wrote here? this is a physicist drawing of, let's say, of a molecule, a complicated molecule or something like that. And inside here, I have some charge density, rho of r. So rho of r, when I say that this object has total charge 0, what does it mean? That some of the density is positive and some of it is negative in such a way that the integral over this small volume will give you total charge 0. That's what I mean, not a charge system. If it would be charged, then of course, if I look here, it will give you something like a Coulomb field. So now we define usual coordinates. One coordinate goes to the element volume, and that is r prime. This is from the origin. The origin is arbitrary. I can put it inside the volume. I choose to put it outside because I'm not Rembrandt and I don't know how to draw it inside. It's just out of laziness. And then I have here this vector r, and I try to plot it slightly bigger. So you see this object has a scale. I called it before d. And this scale is smaller compared to this long distance r. And then there is this vector here, which we can call L. So these are vectors. And we have all these three distances. So what is happening here is that this element of charge, here in this specific box, the charge is either positive or negative. It can be positive. I said everything together is neutral, but here, let's say it's positive, and then, okay, usual Coulomb law will act from here to there. And of course, there will be cancellations, because let's say if you work from this point, then it will be negative. Here it will be positive. It will cancel out in some magical way. But here, from here to here, this is just a drawing of what you know of the Coulomb idea, the usual type of thing. And then in principle I can write it as a formal way. So first of all, okay, there's one more angle, and that is an angle that we call theta prime. That is simply the angle of this triangle that you see. And actually all the multiple expansion, this is the beginning of the multiple expansion, is based on one very famous law, mathematical law that you learned in high school, which is the cosine law. So we have here three distances. I know this distance because this is just the distance to the element. I know this distance because this is the where I'm putting my observer and where I want to calculate the potential or the field or whatever. So I know this theta because these are defined by these two radii, and then I know this L from the cosine law. So the cosine law tells me this square plus this square minus, it's like the Pythagoras, minus 2 cosine theta prime gives you this L squared, right? So we know the L in terms of the R prime and the L squared is equal R squared plus R squared minus 2R R squared. These are not vectors, these are the magnitudes cosine theta squared, which is an ugly equation. You don't need to write it down, but I just remind you what this is. And then what you do is, okay, you write down Coulomb's law. Everything is Coulomb. So V of R is the following. It's 4 pi epsilon 0. Integration, this is a three-dimensional integration over the volume. So let's write it like this, where Griffith denotes d tau. That's dx, dy, dz inside the box. The usual d tau of Griffiths. It's a compact way to write more complicated integrals. Instead of 3 integrals, we write 1 integral as usual. And then we have rho of r prime. So that's the density of charge, which is given in this problem. We are pretending that we know this density. Usually we don't, but let's say we do. So d tau times rho is simply the charge here inside, right? And then what do you need to write here? L. And that will give you L depends on R. It depends on R prime. And that will give you the potential at R. And you see it's 1 over L. That is Coulomb's law. Now this is easy to write on the blackboard, so I'm happy I'm a professor, but to solve these integrals is very difficult in general. But in principle, you can solve it, let's say, numerically. If you have a complicated charge, you can do it, and if the charge density is not complicated, yeah, you can solve it with all kinds of different tricks. Usually you don't do it like this with, you know, you can do it with many methods, with Poisson or whatever, yeah.
What's the difference between R and R prime?
R prime is the distance between the origin to the element of the volume, and then I'm integrating over all volumes. So what I have here in mind is I'm blowing up this, so I have one element, and then I have another element, and then I have another element. So the meaning of the integral is, think about it as a sum. So from this element, you have one distance. Now I'm moving here, I'm changing R prime. So this was the first element, and this is the second element. This is R prime for element 1, and this is the R prime for element 3. And that's the difficulty of this integral, because when I change d tau and I'm integrating on different boxes inside, I'm changing these vectors, right? This is why this is formal, okay? So I'm just writing it down, I'm not solving anything at this stage.
And R, what's R?
I mentioned R is the distance between the origin and the observer where you want to look at the potential. That's the distance. Okay? So you are somewhere in space. I mean, it depends. If you're looking far away, what do you expect? The potential will be weaker. If you're close, you expect it to be higher. And so where you are in space is super important. That's this R as usual. Like in Coulomb's law, this is the usual notation. So then what we do here is, you see this L, what we will take out from it, you'll take R outside, and then you expand the rest, because this integral is over a volume of length, of typical length d. So you know, you are integrating over R prime. This is in the integration of d tau, but R prime is not bigger than, I mean, if you think about it, here it's maybe better to think about this origin inside the box. So the integration, the relevant area of the integration is only of the scale of d. That is a small parameter, so you take R outside, but you have here this R inside also, and you expand. This was already in the TAs, gave you this multiple expansion. I'm not doing it here. And then by expansion, and from this cosine theta, you get some functions. And what are these functions? These are, yeah, the Legendre polynomials. Most likely you're not saying it in proper French, but it's okay. Also, I'm not. Legendre. So you get these series in this expansion, which we are not doing here. And if the integral over the charge, the density of the charge, this rho of R, which has units of Q over meter to the power 3, if this integral is 0, that is, there's no total charge, the leading term is going to be the dipole term. And this is given by, I'm not doing this expansion, so only the leading term is given by this, the dipole potential, which we need in this lesson. So V dipole, so it means the following: VR, the true potential, is approximately at large distances V dipole R. When you come closer, there are all kinds of corrections which we now throw away. Okay? So the next term will be the quadrupole theorem, and it will be 1 over R smaller than this one. So it's negligible at large distances. And this V dipole is equal, and we're going to use this V dipole, and this is going to be the important part that we actually need, is given by this 4 pi epsilon 0 integral over the volume. How do I write it? Yeah, 1 over R to the power 2. So the important thing, the really important thing is this 2 in some sense. because it's not 1 over r, it's not a Coulomb, it's 1 over r squared. So it decays faster than the Coulomb field. And inside we have this ugly object, r prime cosine theta prime, and rho of r prime d tau. So this says, now this is a bit, this cosine theta in principle depends on r. So what we have in here, but cosine theta is always less than 1, bigger than minus 1. So it's not that this is independent of r, this depends on r still in an ugly way. Right? Because you need the r inside, and then for each r you have a different cosine theta, you change r, you're changing cosine theta. So this expression, while it gives you the correct leading term, and this is now this is integration over d tau, and remember rho of r is not 0 in a volume, again with size d, so this gives you something which is finite. It's much smaller, this object, in some sense, compared to the distance r. Yeah?
When you say it depends on r, do you mean r or r prime? Because we can look
It
at
depends
r
on both.
constant.
No, it depends on both. That's exactly the point.
But if we can't we look at r as a constant, and then because the measuring point stays at the same place,
Yeah.
and then say that theta prime only depends on r prime
You,
for a
you-
given r?
For a given r, sure, but that's obvious, because if you fix r, then cosine theta is cosine theta, that's it. For r prime and r, this is the same. But my point is, let's say you want to calculate this integral, and you want to be here, but then the guy wants to move here, then you need to do the integral again,
Yeah.
and that's pretty annoying. So now there is a small, very basic trick. We are going to define an object which is independent of r. What is this object? What is this object? D, which is, yeah, but more or less, I don't know what's D, but
Like the distance between the...
but there's no distance. This is an amoeba. But yeah, you are right. But we're going to define the dipole moment of this object. I think you said it correctly. So the whole idea, so let us define it, and then you'll see how this simplifies a little bit. We define dipole moment. This is the dipole moment of this object, and this dipole moment is a vector. So r prime rho dr, rho d tau. So this is integration over the r coordinates. This is over the volume. So again, you have here rho d tau for this box, then you go around, you sum all of these, and this is a vector. This guy is independent of r. In that sense, you calculate it once and you are done. You can know it. And if you add, if you think about it, what is the simplest dipole that you know from high school or whatever? What is the simplest dipole that you have as the best example that you can talk about even in the middle of the night is one charge positive and one charge negative. What is the rho of r in this case? Sum of two delta functions. So put here in your head, if you can, a sum of two delta functions, and then you'll get your d, which is the distance between these two charges, right? Hopefully you can see this integral. And so this is just, in a university, I like this joke, I say it many times, we take simple things and make them a little bit more complicated. So this is just a more general definition of a dipole that is from two charges. But why do we need this definition? Well, consider, for example, a molecule of water, which looks like a V shape, and here are H, H, and O, and the charges are all over the place, right? I'm not a chemist, but it's H2O. And then you have, these are the hydrogens, and around them there are some electrons with some cloud, and here you have the oxygen. This is a complicated object. We are luckily not going to do the integral of this, but in principle, if you tell me what are the charge distribution, so the protons are fixed and they are like delta functions, more or less, as far, okay, they're not exactly delta functions, but more or less, the nucleuses of these, of the oxygen and the hydrogen are 3 delta functions, which are positive. The total charge is 0, but then you have these clouds of electrons moving here, which by themselves are very difficult to calculate, but let's say we calculated them, let's say from quantum mechanics with a computer or something, and then, okay, this guy has some dipole, right? And how do you calculate the dipole? You calculate the density, and then you do this integral. It's very easy to say, it's hard to do. Okay, so okay, just let's write this. If, for example, rho of r is qz minus d over 2, that is the q minus q. The minus here is because we are thinking of a positive charge and a minus charge down here, delta z plus d over 2, and z is of course the usual z in the z direction. So this is a delta function in dimension 3. So the units of the density is charge over volume, because delta function in 3 dimensions, that's the units. And then immediately rho, the dipole moment is q over d. This is what I told you to do in your heads. I just wrote it down here so you will remind yourself, if you forget about what I said now. So this is in the z direction. There is a kind of definition here that it's heading to the positive one. This is just a convention that we choose the direction of the dipole in the z direction and not in the other direction. Why? Some guy decided, maybe Maxwell, maybe, I don't know who, Ampere, whatever. So one good thing here is that the dipoles, if you have many dipoles, they are vectors and then they will sum up. So if I want to calculate the dipole, let's say I calculate the dipole here on the H, and then I can sum it up like summation in principle, again, like summation of usual vectors. And then, but why is this useful in the context? Let's go back here. Why is it useful? It's useful because you see here I have this cosine theta, which I said before was the pain in the royal. Oh, you shouldn't say these things. It was a big pain because. But what does the cosine remind you? Again, so we have these 2 angles, and it's very important now. How did this? Where is this cosine coming from? What mathematical function? We said it already. Legendre.
The cosine theorem?
No, yeah, it comes from the cosine, correct. Then we use the Legendre expansion, and this cosine theta. When you think about it, when you do the expansion that I'm not doing here, it's in Griffiths and it was in the class, I think. This one, what is this? This is another way to say p. Not p, not that p. This is the polynomial of Legendre. Cosine theta, where I use here L equal 1, and the Legendre polynomial of order 1 is cosine theta. The next order expansion will give you the higher order polynomials of Legendre polynomials. So this is important now. What is important here? This is this cosine theta that comes again from this cosine theorem and this polynomial of Legendre. It's all related to that. It's linear in cosine theta. If we go to the quadrupoles, you'll have cosine to the power 2 and all these things. Then it will be much, much nastier. We don't go there, so you don't know it's nasty, but I'm telling you, it's much nastier. So cosine theta reminds us of something. What does it remind you of? It reminds you of, maybe not, it reminds you of what? A dot product. A very simple dot product, so let's write it. So r hat. The hat is a unit vector. So r prime this is just cosine theta. So by definition, this is these two angles, and I have a unit vector here and a unit vector there, and this is by definition this definition of the dot. This is this cosine theta, and then I can use this because what I can do is I can use this vector, and okay, so let us write it down. And the claim is that the V dipole now is slightly easier, but not totally. P, the dipole, given by this integral, dot, this is the famous cosine, r hat. So r hat again, this is r hat, the direction of r, where you're looking at, divided by r to the power 2. So the idea here is very, it's not that, we started with an integral which has no vectors inside, right? There's no vectors. Here we have a vector, but we call, so it looks like bad because you know, you don't like vectors, right? You like scalars in some sense. We go to a vector, but the benefit here is that this vector you calculate once and for all. It has some direction and it has some magnitude. And you can think about replacing all this junk by two charges in one direction, and you have this P, and that's it. Then you go to, once you have it, that's it. And then, of course, when you change the direction, then, of course, if you look up here, or you look there, or there, or there, or there, this will change, but this is after you calculate. So the nasty integral is in here, given by this integral, which is a vector integral, giving you that, and you are done, and then you don't need to do the integral millions of times. You do it once. And that's very good, and that's why we like this formula. It's very easy to compare to this one, and this is why you have a box here, while this one I didn't put in a box. This is the elegant form, and that's it.
Did you miss R prime?
Sorry?
R prime hat on the cosine theta.
R prime. So there's R prime multiplied by R, but hat. Yeah.
So you replaced it from the cosine theta.
I replaced that in the cosine theta here. Okay, so what I did here I have R prime R, right? This is the definition. And then R prime multiplied by R, this one, gives you essentially this one. See? Then I do this integration, and then I'm left with this R dot, but this vector, the R hat, is nothing to do with the integral here. So I can take it outside, and this is what I did here. So it's a good question, but there's a little small tricks maybe I didn't explain so well, but I tried my best at least. Okay, is this more or less clear? So this is what is done here, and this is the potential, this is the dipole, and now most of the class what I'm going to do is, let's say we have water, it has some dipole, the molecule has a dipole, and then, okay, we can calculate it. Instead of water, let's say you have CO2, whatever, and then, okay, it has another dipole. So I'm now not caring so much where did this P come from. I think I said this already, but I'll say it again. I think about P as like a kind of a charge, but it's not a charge, it's a dipole. And you give it to me and I'll solve it. And the reason is, imagine you are a physicist in the 19th century. They don't even know that there is a molecule. They don't see the molecules. But these are these genius people, you know, Maxwell, all these guys. They imagined some dipoles and they didn't know what they are. Now we know what they are, but that came much later. So that's the beauty of these macroscopical theories, that these physicists were working in a kind of a blind. They didn't know if they were atoms, they didn't know anything, but they imagined some strange something. What I think they imagined was, they didn't know even what is the fundamental charges. So we think today Coulomb is obviously important. They knew that there is a charge, Coulomb, but then they thought, okay, but there are also dipoles, and these are basic things. They exist. they decay like 1 over r squared, and this guy like 1 over r. They not necessarily knew that. Maybe later they understood that, okay, macroscopically I can take 2, but so, and why do I say this? Because we can think about dipoles in 2 ways. One of them is an idealization, and one of them is what we did here. We will usually think about them as an idealization because we are, at least I'm a theoretician. And what is an ideal dipole? So we have, let's say, let's look at this plus and minus thing. And I want this expression to be more or less exact, in my head at least. In reality, it might not be true. As I mentioned, if you are here, then it's not true. But what I can do to make this an idealization, I can take these two together. But how do I do that? Think about it. If I take the plus and minus and put them one on top of the other, what will happen? They will cancel and there will be no effect. So what you need to do to think about it, you need to take this d to 0. What do you need to do to this q? You take it to infinity, and the idea is, in your head at least, you take this q to infinity, this d to 0, and the multiplication of the two remains fixed. That is an ideal dipole. What do I mean by ideal dipole? Then this law will hold even for small r in that limit. Now, of course, you can say, yeah, but what do you mean by ideal? Does an ideal dipole exist in nature? So this is what I was referring before, that if you don't know, if you don't go into the matter, you don't know. So you can think about an ideal dipole, and you can move forward with your theory as much as you want, and then you can think about these ideal dipoles, and it will work pretty good until you reach some length scale that it doesn't work in reality, right? But okay, this idea of ideal dipole, by the way, you have it all the time in physics. I mean, when you look at the let's say Earth revolving around the sun, you say this is a point particle, but it's not a point particle. If it would be a point particle and it has a mass, what would be the density of the mass? It would be infinity. It would be a black hole, and all of you guys will be quetched into that thing. I mean, it's impossible, right? So it's the same thing. I mean, you consider it as an approximation, as a point, and then you don't ask too many questions what exactly it means. But yeah, so you can think about this as something similar, and we will use this. Okay, so this was the dipole. A reminder. I'll later maybe plot the field of the dipole. Okay, so you know that, if you have a charge up here, it will be repelled because this guy is closer. If you are here in the middle, it will be 0, and this is related to this cosine here because the potential will be 0 here on this axis. We will later plot maybe the field of the dipole if we have time. But now let us think, what is a dipole? Now we continue thinking, what is a dipole? And there are 2 types of dipoles in real life. I'm still thinking about some microscopical ideas, even though eventually I want to throw away the microscopical ideas. So, what is a dipole? So I mentioned already the molecule, right? H2O, important molecule. Yeah, you take a hammer. Here is charge, 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 density, that's a dipole, okay? But there are other types of dipoles. What will happen, let's say, if I take out this H and I put it in the ground state? So the picture of the hydrogen atom is this. This is just a hydrogen atom. Let's say in a gas phase. What am I plotting here? The dot, that's the proton. What is this circle? That's the charge density. I'm using here the fact that in the ground state, in quantum mechanics, the ground state of the electron is uniform, it's spherical, it's decaying to all directions. You heard about it. But even, okay, let's say you think about it as something that is rotating here, but let's say it's rotating so fast that I'm averaging it. So I think about it as a smooth charge density. Does this object have a dipole? No.
No.
There's no dipole. There's no dipole here because when I integrate in this direction or that direction over the vector here, so there's no dipole. Then all the spherically symmetrical objects, hydrogen, lithium, more or less spherical. No, lithium is spherical. In the ground state at least, they have no dipole. So this is absolutely true. However, there is something called an induced dipole. And this is important. Induced dipole. Actually, let's say I said that water, one molecule has a dipole. But let's say I have many molecules of water in your cup. What will happen to these dipoles? Just at room temperature, at some normal situation. Will all these dipoles orient in one particular way or not?
No.
The answer is not. In general, it doesn't happen. It can happen in some materials, but in general, what will happen, all these dipoles, these small dipoles will be blah, 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 all over the place. You think about the gas phase, and then in this small element of volume that I was talking before, which contains many molecules of, let's say, water, the total dipole will be zero in a small... So, induced dipoles are always important. But some of them are induced dipoles due to dipoles that existed from the first part, and in some cases the dipole did not exist from the first part. So that is a little subtlety. So let us talk about these induced dipoles. So what will happen when, in a picturesque way, an induced dipole, I use a field. So I take some material, a box, and I have inside hydrogen atoms, and I apply an external field. This external field breaks the symmetry because it has a direction. And what will it do to this hydrogen atom? It will make it into a cigar shape, more or less. I'm totally not exact. I'm just saying what is obvious. Then later we can build a theory. What does this mean? You have a field in this direction, so this is a positive charge, so it's pushed to that way, and the electrons are, one electron is pushed to the other way, so you smear the charge density. What will happen in a weak field? This will change a little bit, and when we make this field bigger and bigger, the smearing, the cigar shape will be, it's not related to Netanyahu, it's just a cigar. It's just going to smear more and more. What does it mean? The size of the dipole increases with the external field that you apply. More external field, bigger dipole. Later we will...
The distance between the charges?
Yeah, the distance will... So exactly, so when I increase the electric field, you get a more dipole. It means actually that I'm increasing this d, if you want to think about this as the distance, the typical scale. It's the same thing. That's why it's called displacement, and there's a field that is called displacement exactly for this reason. So polarization always goes with displacements of charges, always. Polarization is related to dipoles. We will talk about all these things. They're always related to displacements, and this is a displacement of the charge density. So we can ask the question, and we can do a very rough calculation. So let's say that the E, this is the external. Let's write it the external field. So remember, there is the proton and the electrons are feeling the Coulomb fields of themselves, but there is an additional external field that the experimentalist puts in. So let's say this is roughly 10 to the 4 volt per meter. So what will be the size of the displacement? I just want to give you the size. Do you want to guess? The displacement is roughly, we can calculate this, the displacement, so this is the D, which is in the P equal QD. put quotation mark because everything is very rough. This is the real physics. The rest is just making it more precise. This D is like, let's say, this displacement more or less of this compared to the center of this object. So Q, what is Q? That should be the charge of the electron, or which is the same as the charge displacement. So the displacement in this case is 10 to the minus 18 meters. Damn, very, very, very small. But still, what comes and helps you, that in your gas or in your solid, there are Avogadro numbers of these objects. And all of them together will give you a big effect. So even though microscopically you are doing only a very small, barely measurable displacement in this field, which is not, of course, if I go to lower field, it will be much lower. Then I get this displacement. Of course, if I go to extremely high fields, you can break the atom. That's a different story. But we usually will talk about weak fields, in the sense that you are just perturbing this thing and you're not breaking it. You're not ionizing the hydrogen atom. So we need to define some object that will make it more quantitative. So we have the dipole moment of the atom. Doesn't have to be hydrogen. Beryllium, whatever, wherever you want any atom which is spherically symmetric. So it has no dipole without a field. And this is given by some phenomenological, we are in the 19th century, some phenomenological parameter, alpha. What is alpha? Alpha depends on the atom. Atom 1 has one alpha, atom 2 has a second alpha. It's a jungle, and it's a very interesting jungle. And then later, when we will learn quantum mechanics, we might be even able to understand this in a microscopical way, but now we can measure it somehow, let's say. So we can go to, atom 1, measure it, atom 2, measure it, and see what it is. And this is some number. And what did I write here? You see, it's P proportional to E. So this is usually weak fields. So it's not like the water. Does this hold for the water molecule? Answer no. Because the molecule water has a constant here, plus E. So you see, if E is 0, P is 0. So this is for spherical object like hydrogen, etc. only, right? And this alpha is called the atomic polarizability. Alpha is the atomic polarizability. I hope I didn't make too many spelling errors here. And then you can ask. Let us ask what is this roughly? What is this alpha? So let us look at the units. Let's do something simple. P has units of Q times D. E has units of Q 4 pi epsilon 0 D squared. These are just the units. Then P, what do I want? I want alpha. This has units of P over E. That has units of QD over Q 4 pi epsilon, which has units, of course, D squared. So the nice thing is Q is cancelled here, and then this units of alpha is 4 pi epsilon 0 D to the power 3 from units point of view, right? So now, forget about theories, forget about what is the order of magnitude of alpha for the hydrogen atom. So what is alpha divided by 4 pi epsilon? You need to give a guess. Now, of course, equal quote unquote, that is back of the envelope calculation without doing anything. What is it? I divided by 4 pi epsilon 0, but we know what's 4 pi epsilon 0, right? You call it K, I think, in high school. Much better, actually, because, yeah, 1 over K. It goes on top. It's much better in high school because you don't have 3 symbols, you have 1, but never mind. So what is this thing? It has the units of d to the power 3, right?
Yeah.
So now let's say you need to guess what it is. So first of all, you say, I cannot guess what it is. So there is some constant here, which might, more serious calculation. But the constant is order 1. I mean, what do I mean by order 1? 50 is 1. I don't know, I'm not calculating anything. 0.5 is also 1. So there's some constant that I don't know. This is the meaning of this quotation mark. And what is d to the power 3? What is d to the power 3 for the hydrogen atom? What is the relevant scale?
The displacement.
Yeah, but I don't know the displacement because the displacement itself is 0, right? So I need something with units.
Just say that the displacement is 10 to the minus of 18.
What?
Didn't you?
Yeah, no, but I'm actually deriving this. I'm not, here I just stated, this is a statement. Now I want to say what is this alpha. If I know this alpha, then I can find this, right? You are doing, I gave you the answer, now you're using the answer to answer the same answer. You are doing a loop. But someone here mentioned, I don't know who it was, what did someone mention? Yeah, thank you. So it's just basic physics. What has units of the size of volume? That's the volume of the hydrogen atom, right? I mean, that's the only thing which is the proper units, more or less. And what is these units? He said it's a to the power 3. What is a? A is, what is a? That you said it, right? You said A. The radius of Bohr. So this is actually nice because it means that the radius of Bohr depends also on h bar and all these things, but what we have here is the volume, and this will be something like a Bohr to the power 3. What is a Bohr to the power 3? 10 to the minus 30, right? Because in units of meter to the power 3. Because 1 Bohr, 1 angstrom is roughly 0.5, but forget about the 0.5. So this is the size. So this object is roughly 10 to the minus 30, roughly 10 to the minus 30 meter to the power 3. And this gives you alpha. And now I go back to you. Yeah, if I roughly, from that maybe I can calculate these numbers. Because if I know alpha, then I know the displacement, I know everything, right? So I'm closing the loop without doing the calculation. And we can do it slightly better than this, with some microscopical picture in mind. And the idea is like this. Let us say this is when the field is 0. This is the hydrogen atom model. We invent the model, not a Bohr, not a sophisticated model, a simple model. And now we have, no, I'll do it a little bit differently. I have an ellipse. Ellipse is awful, right? We hate ellipses. So we define a model. This is the tricks of the theoreticians. This was the charge, and now we're just going to move this one only. It's of course cheating because everything here is very rough. So I'm moving the plus, okay, a little bit because of the external field. This is when E external field is not equal 0, just to get a feeling of this problem, and then it's going to move, and then I'll have this displacement d. But now we can use, and I'm assuming the electrons are, nothing really changes. Why do I assume that? Because I say, okay, the effect is very weak, so nothing really is changing. So what will I have here? this is the location of the plus charge. Now I will, maybe I should write it in a different way so you can see. This is the effect, but then I have this motion to this plus, and then what I'm going to do is I'm going to build here a sphere inside. I mentioned before that this is 10 to the minus 18, so this is not a good scale because all this is 10 to the minus 10 meters. That's the size of this object. And what do I have inside here? I have inside here some density, rho. What happens to the density outside here? You don't care about it from the point of view of the field that this guy is feeling, right? You throw it away because this is like, we make it a sphere. It's not exactly a sphere, obviously, but this is the charge. Now what is this charge density inside this thing? So first of all, what is the radius of this thing? This is this d, right? This is what we are looking for. If we know this d, then we know the size more or less of the dipole. So what is this density? This density is more or less, of course, let us always write here like this. This is the charge divided by 4 pi a squared, a to the power 3 over 3. So what is a? This is this sphere here, the size. A was also, this is the electron is smeared here, right? And then you have a charge of the electron and it's inside this sphere, and I say, okay, it's uniform, which is also not true, but I don't care. You understand this or not? This is trivial. Forget about the proton. You have just charge of the electron smeared here. You have one electron inside this ball. This is the charge density, and it's uniform. It's the charge divided by the volume. That's it. Is that clear?
You're talking about the entire
this
volume of the hydrogen atom?
Yeah. This density is also here.
Okay.
It's everywhere, but the density here, you don't care about it. Because according to Gauss' law, if I want to calculate the electric field on this guy, we are looking at the charges inside. The outside is not important.
But inside, aren't the charges zero?
Inside the charges are not zero because we have this displacement. So what is the charge inside this small sphere? It's very easy.
It's a delta function.
No, it's not a delta function. I'm not talking about these are the charge of the electrons. It's the rho, which I had here. Sorry, this is the charge. Q inside this.
So you're assuming a uniform charge density across all the...
Assuming this, every time there is an assumption, I make it the simplest assumption I can do.
Okay.
And there is a uniform charge density, and that means that I can replace the charge inside this object, which I don't know its size. I can replace it with a delta function on the origin. This is basically Gauss' laws. And then this is this rho multiplied by 4 pi over 3 d to the power 3. So what is this charge? This is I just will cancel it here. This is Q d squared d d to the power 3. This d to the power 3 divided by a to the power 3. So the electric field on the proton now is composed of two things. What is the electric field on the proton? It's the external field, and due to these charges inside here. So I'm going to balance them. That will be the equilibrium. This is how much you are moving, and that will give you the displacement. So what do I have here? Let us write it.
Can you repeat that, please?
Sorry?
Where you have taken the proton and smeared it.
No, I
Where
took the electron is smeared, but it's always a sphere.
The black sphere is the electron or the proton?
No, the black sphere.
Because
This is electrostatics. If you have a uniform charge density, this is something you learned in high school. If you have a uniform charge density and you don't care where it came from, and I look at some point inside, what you care about is the charges in this Gauss sphere.
Right.
And this is what I'm taking, because what is outside is not influencing the field on this proton.
Okay.
So I'm just taking the charge here from the electrons in the middle, and that's it. And the rest is not important from the point of view of the electric field on the proton that is here.
But outside the red sphere, isn't it the electron? Isn't it some drawing of an atom with the proton inside and the electron outside?
No. What is a hydrogen atom? A hydrogen atom is a charge which has a point.
Proton and electron.
Yeah, electrons. So these are the electrons.
You said that,
All this is the electrons. But the effect of only these charges in this sphere on this displaced proton come only from there. What is the question?
I think he's asking, he's looking at it as an electron circling the proton.
sing-
But this is
I'm
a
not
charge
looking at this
density.
as
This is a charge
electron
distribution.
is. I'm thinking here like in a, okay. This is what I mentioned before. I'm not thinking of the electron as a point. I'm thinking as the electron as a smeared object, like in quantum mechanics. There is some cloud, and this cloud, I'm taking it to be uniform. Inside the radius of Bohr, this is what I said before, that this radius of Bohr has to do with quantum mechanics. So if you want a different way to say this, that all these effects, they come really from quantum mechanics. But I think you did, you know from your vacations in the pub, that a charge of a hydrogen atom in the ground state is kind of smeared outside here. This is something well known in, let's say, in first year courses, like say, ideas of modern physics or whatever. I mean, this is something you learn. It's essentially what is what is rho? It's essentially the charge of the electron multiplied by psi absolute value squared, which is the wave function. But that's the way this thing thinks. So if you don't know about this, just look at ChatGPT. What is the charge density of, or what is the spread of the electron inside the hydrogen atom? And it looks like a sphere. It's decaying in space, but I'm taking it to be constant. I think you know this, right? I mean, this is kind of well known, I think. So anyways, let us balance these two forces. So this charge has two forces acting on it, one of the external field and one due to the charge density that is left here inside. So the E on the positive charge, which is equal to the external field, is 1 over 4 pi epsilon 0, as usual, rho times 4 pi d to the power 3 over 3, divided by d squared. That is simply the Coulomb's law from high school, actually. So this is equal to 1 over 4 pi epsilon 0 q, this is what we wrote here, over 4 pi a to the 3 over 3. So a is again the size of the atom. This is more or less the radius of Bohr, 10 to the minus 10 meters, multiplied by 4 pi d to the 3 over 3 divided by d to the power 2. So you see what happens, this one and this one and this one and this one will cancel. And okay, this is equal to, let's write it in absolute value. This is equal to the external field. What is the external field? The field that the experimentalist is adding from the outside to create the dipole. And the dipole is related to this d. And you see the nice thing is d squared and d3 will cancel, and here I'm going to be left with d. And you see that d is proportional to E. And that's exactly what I said at the beginning. The bigger is E, the bigger is d. Stronger field, more stretch, that's all. So you see d is proportional to E, and if d is proportional to E, and you have q times d, what is q times d? That's the dipole, P. So if I summarize all this, and I didn't make too many mistakes, I have that the dipole moment, P, in absolute value only now, is the external electric field, E external, and now I need to multiply it by a to the power 3, because again, this is Q times D. Here I need to multiply it by a to the power 3, this one, and I need to divide by, we can put this on the, okay, we can divide it here by 4 pi epsilon 0. Now I can multiply by 4 pi over 3 and divide by 4 pi times 3. Then I'll get a to the power 3, 4 pi over 3. That is what? The volume. That's the volume of the hydrogen atom, more or less. So P in absolute value is, then I remain with this free volume of hydrogen atom times the external field divided by 4 pi epsilon. So what is alpha? This is this coefficient. It's 3 times the volume of the hydrogen atom. And you can think about the hydrogen, the volume without the distortion, right? 4 pi epsilon 0. And we can put a quotation mark because this is a very rough estimation. But this is what exactly I said before. I said before I said this alpha has d to the power 3. So now we see this is the volume of the whole object, not the volume of the displacement. That was the tricky part before where I cheated, because I'm saying here this is the volume of the atom. I did make some mistakes in the way.
4 pi epsilon 0.
Yeah, there's no 4 pi. There's no 4 pi. Why not? Yeah, because here I have the 4 pi already. So then if I added it here, then I had to this one you don't need it at all. You just need to multiply by 3. So this is not needed.
According to this, you need to multiply it by epsilon 0.
In the volume, the 4 pi is in the volume.
But
This is okay. This is fine. But this is minor. This is fine. You can check it later, and if you see a problem,
but
come back.
you multiply it by epsilon 0, and here you divided it by between those
This I made a mistake. P. I just use this equation.
I'm talking about the red one.
This one.
This one. You have
Here.
here you have
This is
multiplication
history.
by epsilon 0, and here you have division.
No, but here this is just the units. You say the units.
The epsilon 0 should be on the denominator.
The alpha. Oh, where did I make a mistake? 1 second, you're right. This is, you're right. This here is wrong. Because I take the epsilon to this side. This is epsilon 0. Thank you. This is important. Again, this is just units. And you see the units are correct, but now I said something else. This is the volume of the hydrogen atom. This is, of course, monkey business. This is not correct. The real life is much more complicated. What is the real life? Well, let's go and measure. But it does give you the correct order of magnitude, because this volume is, again, 10 to the minus 3 Armstrong to the power 10. That gives you 10 to the minus 30 Armstrong. So this thing is giving you the order of magnitude of things and not more. But unfortunately or not, different atoms behave differently, because what did they do for a spherical atom? It's like taking a cow, a horse, and an elephant and saying they are spheres, which is not correct. But it is a good thing to do. You first do that and then you correct. So let's go to the experiments and let's see what is this alpha. and see that it's more complicated, which is not so surprising, but this gives you some rough estimate what's going on. So you look at the table, and this is this, for example, alpha divided by 4 pi epsilon 0. So like here, I divide it, so what I'm getting here is this 10 to the minus 30 meters to the power 3. This is the units. And this I got, from this calculation I got this. You can imagine what a physicist that finds this in the 19th century, and he has no clue about Bohr. It's like, where does this crazy number come from? But we understand it now because we know that Bohr says this is the size of the atom, right? So there is a connection, but no one saw, okay, I don't think anyone saw the connection. This is the size of some object inside. They just measured it, and they got this incredibly small number, 10 to the minus 30 meter to the power 3. Okay, again, because this is a volume. And then let's say we have different atoms. So H is the hydrogen, and here the prefactor based on measurement is 0.66. This is measurement inside the gas phase. All the atoms are far away one from another, so they are not interacting. This is, you have one electron, here we have 2, that's the helium. The helium is 0.2. It goes down a little bit, you can think why, but it's not so important, because if I go to lithium, lithium is 3, which means 3 protons and 3 electrons. This one is 24.3. Then I go to beryllium, which is 4, this is 5.6. Carbon is 1.8. Argon, which is 18, this is 6, I think many of you know, this is 1.6. And then potassium, ashlegan, which is 19 in the, yeah, this is 19 electrons and protons, this is 43.4, doesn't matter. So what do you see here? You see here, what do you see here? What is this? What are these numbers reminding you? The real life is not hand waving. You see here more or less what do you see? Some Russian guy, not a French guy. Mendeleev. I mean, you see here a little bit the periodic table, a little bit. You see some connection, but of course when they measure this, so what is helium and what is argon, for example? Maybe you know, even though you're a physicist. These are the noble aristocracy from, I don't know, from France and Russia. So these are the noble guys, and the nobles, you know, if you insert on them a perturbation, which is the external field, what happens to a noble? You know, we also have financial perturbation on the rich guys. It doesn't do things, they don't care about it. So the same here. So you can understand it more or less. What is a noble gas? It doesn't interact with anything, right? It doesn't care about other guys. So it doesn't care also about external fields. And microscopically, this is because of Mendeleev's table of elements, where we understand it today. There is, let's say, you have, let's say that for the helium, we have 2 electrons which are occupying a surface, and they are very robust. While if you have a lithium or if you are in potassium, what are these? These are the last part of the table of elements, and they are very susceptible to give you an electron, right? They are very generous. You can tear out an electron, not in this experiment. I mean, they like to react. I mean, this is these very reactant things. So you see this, and of course, what I said before is not exactly what did I say before? It goes like the volume. What does it mean goes like the volume? This prediction is very bad. You see, it doesn't go up straight because this guy should be bigger than this guy, right? It's not going up at all. So my prediction is horrible, but is it really horrible? No, it's fantastic. It's fantastic because it gives you the right order of magnitude, but nothing else. The real life is more complicated, and okay, you get these numbers, and then you need a microscopical theory to explain what is this alpha. Okay, so so now what about molecules? So now we just talked about atoms. What about molecules? So I mentioned the H2O, so they are molecules with a permanent so H2O, for example, some object that looks like this. It's not an alien from outer space. This is H, this is H, this is O. This is a permanent dipole. Even when E is equal 0, the external field is equal 0, it has a dipole. With molecules, it can be also more kind of more complicated, because this I just remarked this object for some systems can be a tensor, it can be a matrix. The reason is that if you have a molecule, let's say a line, and then you apply a field like that, or you apply a field like that, it's not the same response. So I'll just mention this, like for, let's say for CO2, you can read about this. Alpha may be a tensor, may be a matrix. So it's more complicated than what I said. But now, let us, so what I did up to now, I said there are symmetric objects like the hydrogen atom, and there are these molecules which are not symmetric, they have dipoles, microscopically. Now the question is, do we need two theories when we go to macroscopic objects? It looks like it, because one of them has dipoles and one of them doesn't have dipoles. But it's not like that. We can treat all these different points of view on the microscopics. When you go to the macroscopic picture, the same. Which means that sometimes things are fundamentally different on the microscopic level, but when you look at many of them together, you don't care. And this is the disadvantage, you can say, this is the disadvantage of the macroscopic theory. You see something and you don't really understand what's going on, and this is true. On the other hand, it's also the beauty of the macroscopical theory, the thermodynamics and what we are learning now, electrostatics in matter, that the people who were talking about this at the beginning, they didn't have a clue what they were doing, but all the systems, it doesn't matter, molecule, atom, all of them are the same. Let me explain why. Because let us now think about it like this. Let us think of, let's say we have permanent dipoles, and I put it in a gas, in a box. And then I have dipole 1 is like that, and then dipole 2 is like that, and then dipole 3 is like that. So, etc. So inside, if I look here inside the box, which contains inside many microscopical dipoles, they will be all oriented in all different directions, and the net effect will be zero, no effect. However, I can do something. This is when the external field is 0. Now I can do something else. I can add a field. And then something will happen. And what will happen, you will orient all these micromolecules, which had a dipole from the beginning, and they will be preferring one direction. Let's say you point this way. So with the field, you can, in some conditions, which depend on many things, like pressure, temperature, it's a very complicated thing, Now you have a field in this direction, and now maybe all plus minus, this is an exaggeration of course, plus minus. What do we mean exaggeration? You don't need that all of them will go in one direction. You can have some of them in this direction, but more preferable in one direction. Now you see that the effect, the macroscopical effect, is the same, because here I induce by the external field, I induce a macroscopical dipole. Without the external field, there's no dipole on average. So the effect of these things are very similar. So this is great because now I don't need to talk about water and about hydrogen. I can talk about all of them together. They respond somehow to an electric field, and I don't know how. There is some coefficients like this alpha, but the meaning of the dipole is not a microscopical dipole, but some local environment that contains many dipoles inside that without the external field will give you zero. So this is what we are going to do. So
when you say that we have a constant that helps us describe the dipole in these materials, you mean it describes how much the material is susceptible to be influenced by the electric field?
exactly.
Because the more it's susceptible, the larger the dipole, the total dipole will be.
Yeah, and we will formulate it soon. I didn't formulate it, but there is a fundamental difference. You see here, I had this table. This alpha was given for hydrogen, for different. It did not depend on macroscopical things like temperature, volume. That's a difference between the two things. What the alpha can or cannot, depending on the microscopics, and the conditions depend on in a very complicated way on things like temperature for these type of systems. So for example, if you want a solid state device, maybe you have regions in space where you have dipoles in this direction, and then you have here dipoles in this direction, some grains. All these grains are super microscopical usually, and they are all pointing in all kind of random directions. This is a granular material, a solid but granular. But when you apply a field, then you'll have a preference in one direction, and then you'll have a macroscopical effect controlled by the field. And the same with the gas or liquid. So whether or not they existed, or whether or not they existed on the one level or cancelled out, it's not so important when you deal with macroscopics. But then of course when you change parameters, you can try and measure this, and you'll see does it depend on temperature or not. This is a different thing, but we are not talking about that. Just to understand a little bit more about this. So let us remind you, hopefully, or maybe give you to some further reading in chat if you don't know this. So let us. Why am I saying that the dipoles will orient in the presence of electric field? Why do I say this, and why do I say then this will depend in real life on things like temperature? So let us remind ourselves where it comes from. So let us think of the simplest dipole in the presence of an electric field. So here I'm giving you the picture of the dipole existed from the start, right? It's not the hydrogen. This is my molecule, a physicist molecule with two charges only. And then you have here a minus, and here you have a plus, and this is the dipole. You think about it as a rod in between, charge here, charge there, and then it's rigid. You cannot, they are not moving, you cannot change it. This is the molecule in the sense, the charges here and here, etc. But now I'm simplifying things. This is like this, and this electric field is the external electric field that is applied here, and this, what I plotted here, this is a plus. So there's a force in this direction, and then this guy is a minus direction. Let's put here the origin, and what do you get here? You get a torque.
A rotation.
You get a torque, and in principle you get a rotation You can ask, will it really rotate when it interacts with many other things? The answer is not always, but in a gas it will, in principle, rotate. And we can calculate, okay, we can call this d plus, this vector, and then we can call this vector d minus, and the total vector which connects these two guys is d. That's what is d? That is the size of this object. For the molecule water, that will be more or less the size of the water of the molecule, and then you know, the n or the torque. Sometimes I think it's with tau. This is simply given by d plus cross QE. So what is Q? Q is the charge up here. There's a plus charge, and down here there's a minus Q. Minus d minus. This is the vector cross QE. And this is easy to understand. This is d over 2, because it's in the middle. This is also d over 2, but with minus sign. Then this guy is equal, this n, this is a kind of well-known equation, is d cross E. So, because of that, this object is going to rotate. This is the torque.
No, P
What
cross
happened
E.
to Q?
What is the
P
Q?
cross E, no?
Q is gone.
P, yeah, times Q here.
So P is a
And P,
The Q.
is a 10 as a
yeah.
is a top.
No, he's correct. Sorry.
P shall
And not momentum, this is the dipole. That's the whole point.
Okay.
P cross E. I forgot the Q here. Thank you. So, give me the dipole. The bigger the dipole, which existed from the beginning, it's not an induced dipole. But in principle, it can be also an induced dipole. This P depends. Cross E. Now, this is the torque, and this gives you what? The change in the angular momentum. dl dt, like Newton's law, dl, L is the... And this will cause you a rotation. Now, what is P cross E? P cross E is absolute value P, E, times sine T.
Sine theta.
What is the work that you do? You need to do like FDL for linear things. Then you have the torque times d theta. So you have sine theta d theta, right? You integrate that when you turn to get what? The work or the potential energy. Integral of sine theta, the sine again comes from the cross, gives you cosine theta. So when you do this, you get this simple and well-known formula for the potential energy of this object. Sorry. Again, if you don't know this, it's very important actually, but you should read about it in ChatGPT or whatever. This is the potential energy of this object in this electric field. What does it mean? It means something very simple. P is the dot. And this is the important thing. So, as a function of theta, theta goes between 0, let's say E is positive in some way. So you have here minus P is some number. This here, before it was a sine, here it is a cosine, right? So yeah, it's minus a cosine. So it starts something like this. A cosine starts from 1, so this will be minus 1. It will start like this. Something like that. And you have these stable points. But this is also obvious from the torque, because if you are pointing like this, the torque will always put you back. So these are the points of stability. And what does this mean? It means that when cosine theta is equal 0, then you are at the minimum of the energy. Right? Because then cosine theta is 1, then this is the P is positive, let's say E is positive. You are at the minimum of the potential, which means that you want to align in the same way. So what will happen when you add temperature to this picture? If you have many of these dipoles at low temperatures, they will want to align. But if you increase the temperature for Boltzmann laws, they will not care about this energy anymore, so they will not align. So the alignment depends on temperature in real material, and there can be phase transitions where sometimes they align and sometimes they don't align, because if the temperature is very high, the kinetic energy, all the fluctuations, you don't care about this. But at zero temperature, you want to align. So it's very sensitive to temperature when you have many, because again, the idea here comes from statistical physics and thermodynamics. A system at low temperature wants to go to the lowest energy. And that means alignment. At high temperature, it's not like that, because everything is moving and everything is fluctuating. So this proportionality, in principle, should depend on, when we talk about these objects, should depend on this, but you have a preference depending on the electric field. So all these things are things to be thinking about, but now we're actually going to kind of, maybe unfortunately, maybe not, we're going to ignore them in some sense. And what we are going to assume now, after the break, let us assume now that we have a material which has a field. This is a very important field that is new for you. It's called the polarization field. So this is where we're going to end, is polarization. So usually assume a field E is applied on matter, some matter, we don't know what it is. We get an induced dipole moments. Repeating myself, it doesn't matter if this was caused by shift of the electron structure inside the hydrogen atom or because just caused some alignment, we don't care. The material for our purpose is defined with a new field, with the polarization field. This is big P. Before I had small p. So this is small. Big. Not to be confused, big P.
You can do a leg to the P.
No, I can't. So this P is defined. Oh, it hints that a break is needed. So these are the dipole moments per unit volume. The sum of the dipole moments per unit volume. So this is like a charge density, but it's like not a charge density, it's a dipole density. So what does it mean? Let us define it a little bit. Now, what we want to do is, somehow we got this P. What did I say up till now? This P, it's a bit confusing, maybe will be proportional to E. And now we say, okay, you have this P. How you measure it, you need to measure all the dipoles in principle in the system. How you do it, I don't care. Sometimes it's possible. But what is this dipole moments, sum of dipole moments per unit volume? It's like this. We have an object, and then we have a delta tau. This is the precise definition, and then we have this delta tau. And inside this object, we have all kinds of microscopical objects. So this box is infinitesimal, but it's really we take these idealized dipoles, so they are points, and then inside there are many, many small dipoles, and this polarization in delta tau, so the polarization can be something here, can be different here. It can change over space in a very complicated way in principle. So this is a function of x, y, and z, like a charge density, which could be a function of the space. This is the sum of the microscopical this micro is these dipoles that we had before, some of them inside the box, divided by the volume of the box. So if you have a lot of dipoles, let's say they are all in one direction, this will give you some number, and here let's say you have less dipoles, it will give you a different number, and then this polarization field will change in time.
Right? An average of the dipole.
It's a kind of average, yes, and yeah, if the system self-averages, it's an average dipole. So I'm using here many things. One of them is that these dipoles are vectors, so I can add them up. I'm assuming that this box is big enough, the small box is big enough, so to replace this with a smooth function. So eventually what we will have is a smooth function and not a crazy delta function changing function. But this is exactly the same that we did with charge density, that were delta functions. So eventually what we have is some smooth function. But what is the simplest smooth function? So for example, what we want to do is we have a polarization of a sphere, which means the dipoles are in the sphere, and we want to know, for example, this someone gives you, we want to know what is the electric field outside here or inside there. That is the question. So again, I'm repeating myself, we replaced, all this lesson was, we have now this field, which is like a kind of charge, how to calculate things. We need to build a new theory. Because we know, if it would be charges, I know how to do that, right? In principle. But if it's polarization, I don't know yet. So go to a break and then I'll teach you how to do it with a polarization field and not with a charge. Of course, the big difference is now that if you think about this as a kind of generalized charge, but this is a vector. So it's more complicated, it's not simple. So we have a material which has a polarization field inside. It has some arrangement of dipoles. Forget about the origin of this polarization field. It could be created by some electric field, but it could be also in a material called ferroelectrics. What are ferroelectrics? They are essentially like magnets, where all the dipoles are more or less oriented in the same direction. Thanks. So we have this polarization field, and it's a vector. I tried to explain how it is constructed, but I just defined it. In some sense, if you want to think about it, it comes from God. I don't care where it comes from. It's there. What is the field outside and inside this object in general? So the problem is twofold. First of all, we have a vector here and not a charge. Not a charge which is a scalar. We have a vector that is creating a potential, creating a field eventually. And secondly, these are dipoles, so there's no Coulomb law. So this is very bad. We need to start the course from the beginning, right? So the answer is no. We always like to go back to old problems if possible. And we are going to show you now that starting with this field, given that field, we can go back to the usual type of electrostatics. And this is very elegant in my opinion. So let's say we have this function P in this domain. Then I'll just first of all give you the claim. The potential, oh, this looks good. The potential at point R, what is point R? Somewhere here, wherever. If I know the potential, I know the electric field, it could be also inside, is given by two things, some rho b and sigma b. What is rho b and what is sigma b? Well, we still need to relate it to the polarization, but rho b is some charge density. Sigma b is a surface density. So what I'm doing here, I have here a complicated polarization field. I'm saying this is equivalent to a problem where you have some usual charge. These are like the old Coulomb units of charge, the volume, and these are usual charge meter squared. Of course, these could depend in principle on position, and it could be very complicated. But this problem in principle I know how to solve, right? Because this is the old problem. So the question is, how do you go from this vector to this thing? What is the symbol B? This is called bounded charges, effective charges. They're not real charges because they come from dipoles, even ideal dipoles, but this is very nice because, yeah, we kind of, in some sense, solve the problem if we understand it at least. Because what is rho of B? Rho of B, I claim, is div P. Remember, this is the dipole per unit volume. If you look at the dipole has units of Q times displacement over volume. When you take the div, the units of the displacement are gone, so it's Q over volume. That's the correct units at least. So give me this P, and then you get this effective charge density, and sigma B is simply the polarization times n on the surface. So this object, you know, you have some polarization here. Let's say it's in this direction. So this is polarization in this direction. N is the normal to the surface. P dot n is just the P. But of course, if the polarization here is like that, then the n is going in 90 degrees, then that will not give you a surface density. You need to, in principle, know all the polarization on the surface and everything inside to calculate div P. So for example, if P is a constant, what happens? There is now no charge density, because div P is 0, and you will have only charge on the surface. Before we prove this, and we will prove this, because this is the basics, because in some sense we solve now the problem if this is true. Let us see that why this makes sense, about kind of the hand-waving argument, with some examples that I can draw on the blackboard. So let us say a physical picture, more or less, hand-waving, is like this. Let's say I have a system with plus, minus, no, I don't want to plot so many, plus, 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 minus, 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 minus. This is a dipole, right? So what I'm plotting here, plus and minus, you can think there is a stick in between. This is the dipole of the first layer. Now let's put another dipole layer here, plus, 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 and then there'll be a minus. I'm not plotting the sticks, plus, minus, etc. What will be at the end? Minus, 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 minus. So the idea here, first of all, what is it? The P here, the polarization field, is a constant because I try to plot it as uniform as possible as I can. So this is only one simple case, but the idea here is kind of simple, is that these charges of the head groups, if you want, this and this, will cancel. And then what we are left with is a system with plus up here and minus here, these are the charge densities that are left behind, and then you don't care about all this junk in the middle, you just care about this, and then you solve this problem. Again, P constant, div P is 0, no charge in the middle. There is some polarization here, because if I create here a box, there is a polarization, and this constant will give you the numbers. What is the effective charge on top here? This is the sigma bound here, which, notice that the sigma bound is such, in this is a simple example, the total charge of the system in the effective system. So this is the real system, and this is what we solve. The total charge in both systems is 0. So every dipole has total charge 0, and eventually what we have here, charge up here and charge down here, but it's the same amount of charge, so the total system is neutral, which is also to be expected. If you have something more complicated, which I might fail, this was when div P is equal 0. But if I have something like this, plus, 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 minus, 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 minus. So this is a dipole. This is one layer of dipoles. And now let's say you have plus, minus, plus, minus. So here there is nothing. So why do I do that? That means that the div P is going to change, right? Because the density here of the polarization field and here is different. It's changing in space. Now what happens is that some of these, we can look at which ones are cancelled. This guy is cancelled. This guy is cancelled. And if you think about it a little bit more, it depends how you continue, of course, then you are left eventually with something like, so this is truth, this is effective bounded charge, again, bounded is this letter that we have here, B and B. This is what we have eventually in the theory. What we will have here is like something like these guys will cancel. Of course, you have the usual, like before. You'll have the charge density. This is sigma B. This is not changed because let's say the polarization is changing in space. Div P is not 0, but there is some polarization on top, some polarization on the middle, on the bottom. So this is this layer that I'm not cancelling with anything, but these two guys are cancelled, and now I'm left with these three. So I wipe out those in the circles. And okay, then I need to continue this, and then you'll have here somewhere some pluses and then minuses. And these guys are my picture of rho B.
When you say
This
that,
is in hand waving. But now we want to prove this and so that this is exactly correct based on math. But this is more or less the general picture. Yeah.
when you say that two charges cancel each other, that it's
In this
because-
picture, at least,
in
yes.
this picture, it's because the distance between them are
Yeah,
much
I
smaller
made
than
it smaller, so I made it much
compared to the-
smaller. So this is certainly not a general proof of anything. This is just a way for you to start thinking about it. It's a pedagogical tool. In this special example, you can imagine how this comes up. That's all. To prove this, we need to do something. This is nothing. This is just a picture on the wall. So let us start with a sanity check. So I have this effective picture with these bounded charges. What we expect, and what I mentioned already, is that the total charge in this bounded charge is 0. So so you have some charges inside and some charges on the surface, but both of them are related to the polarization. They are not arbitrary, and somehow they should give you total charge 0. And this is easy to prove. This is not a proof that this is correct. This is just to check that common sense is working, that the total system is neutral, the effective system is neutral. And this is easy to prove with the divergence theorem. So I integrate rho b over the volume. This is the total. What is this? Is this the total charge? No, this is the charge inside the material. Only this charge. So this is QB. What does this have to be equivalent, or what we expect it to be equivalent to the charge on the surface? So let us use this. So is this, I claim this is the same as dA, A, PdA. This is now on the surface. This integral is a two-dimensional only on the surface with a minus sign. Why do I do this? This is this sigma b. This is the charge on the surface. Okay, this bound is maybe not good inside. This is the Q of the surface, if I believe this equation. But if I use the divergence theorem, then this is simply given by minus over the volume div p d tau. So you identify this. So what you see here, that if this one is correct, then this one is correct. And then the total charge is 0. So again, this is not a proof. Now we're going to prove that these two things are correct, but this just says that the charge inside, the charge outside, if I put here these definitions, will give you the same answers. There is a different sign because one of them has a minus, the charge, one of them is minus the other, right? So the total is 0. Okay, so let us prove this following Griffiths. We are now at Griffiths chapter 4. In the class, in the homework, we are already started magnetic field also, which is 5. So you should read these chapters. So what is the, in a nutshell, what is the idea of going from these vector fields to these scalar fields? What do we want to do? We want to go from dipoles to charges. Dipoles decay like 1 over r squared. Charges decay like 1 over r. How do you go from one to another? If you have 1 over r and you want to do 1 over r squared, you differentiate. So we need to use some differentiation. This is what we are going to do. Essentially, that is the whole idea, to go from this polarization back to the charge picture to differentiate. It's a bit more complicated than that because you need to, you have vectors here. Okay, so we are going to use two identities that are simple identities, which most likely you know. A grad of 1 over r, it's a vectors, sorry, grad of 1 over r is r over r squared. Or more correctly, I want grad of r minus r prime is equal to r minus r prime hat. So this hat, again, it's a unit vector in the direction of r and r prime. And I think you know what I mean by r and r prime eventually, but these are just two vectors in space now. This is math. Divided by r minus r prime, absolute value squared. Where grad, as you know, is simply x d over dx plus y hat d over dy plus z hat d over dz. So what you do is you to to prove what I'm going to to prove this is very easy. What you do is you say R is x, y, z. What is R prime is x prime, y prime, z prime. And then what is R absolute value is you need to take x minus x prime squared plus y minus y prime squared plus z minus z prime squared and take the square root. Then you need to apply this, which means take derivatives with respect to the function, and then you get this thing. It's very easy to show this, and I leave it as an exercise. So this is what we're going to do. It makes sense because, and you saw it maybe, you saw it somewhere. And if you don't remember, then I claim you saw it, but you don't remember. So then this will be called Aleph, and I'll use it soon. Then there is another very simple relation, and that is div of fa. What is f? Some function, scalar of x, y, and z. What is a? It's a vector field, but arbitrary. This is some math. So what is this? This is just taking derivatives of multiplication of two functions, more or less. Of course, a div is a div, but you know what will happen. It's like the taking the derivatives of products if they were scalars, but okay, it's a bit more complicated. But then this is simply f div a plus a grad f. If you're very much interested in the details, this is in chapter 1 in Griffiths, but I think it's obvious because again, you have an operation which is derivative two functions. Okay, one of them is a vector, and then you have, once you take the derivatives on A, and once you take the derivatives on F. So I think it's very intuitive. Maybe the details are not so clear, but I think this is good enough. And this is the other thing we are going to use. So now comes the physics. Up till now I didn't do any physics. Now, what is V1? What do I mean by 1? Inside my material, I have some one dipole. Then I need to add all these dipoles, right? But this V1 dipole, I told you what it is. That was in the previous class. This is, I'm going to write it like this. P with, this is small p. This is the real dipole, not the polarization field that don't have the same units. So this is just the dipole of this one dipole. Not to confuse with the capital P. Then we said, okay, we need to multiply this by r minus r prime. This was the trick in the last lesson, and then you have here 4 pi epsilon, r minus r prime, vectors, to the power 2. And again, this 2 is the whole business here, instead of 1. So what do I mean by this exactly? This is more or less the same as before. Here I have r prime. This is my origin. It's arbitrary. I can put it in many different ways. This is r prime. This is r. And this is r. Here I have my viewer, and I'm interested in v at point r. So this is one dipole, this dipole here. And what do I need to do? There are many dipoles inside, right? So I need to sum all of them. What am I using here? The superposition principle. And then I'll get the potential here. That's all. In principle, it's what you need to do. So now the first thing is, what is this microscopical P? What we will do. In some sense, in the real life, this is like a delta function on some point, if these are ideal. But what we are going to do is we're going to say this is the field which depends on r prime, right? X prime, y prime. So this is the polarization field multiplied by d tau. So what am I doing here? I have in this box here, I'm summing up all these small dipoles, giving you the polarization. This is not from one, but this is from some of many. This represents an average kind of dipole. If you want, this is the definition that I wrote in previous class. The dipole at the effective point is the dipole the macroscopical d tau, that's the units, right? This is dipole per unit volume. I multiply by volume of this small box, and I get this dipole. This is all the thing I wrote. So now what do I need to do is I need to do the superposition principle, which means I need to integrate over all this r prime. And remember also this p depends on r prime, because I integrate over this box, over that box, all over the place, and then I'll get the answer. So what is v of r in principle from all these dipoles? It's 1 over 4 pi epsilon integral now over the volume. This is the sum. It's a sum over the amoeba in which all these dipoles are sitting. One vector, one integration, but it's actually 3. And then you have the volume, d tau. This is the x prime, dy prime, dz prime, usual Griffith's notation. And then I need to write down p r prime. This is the big P. So again, this times this is just the dipole, which you have here. Dot r minus r prime hat divided by r minus r prime absolute value, again to the power 2. If we had here 1, then it would be boring. Okay, so now what do we see here? We see this object here. This is related to Aleph, right? So I can replace this object here with, I need to not forget the dot, by this grad of this function.
Minus?
The minus, yes. And so let's do that. Oh, no, okay. So there is a, thank you. So I nearly forgot. When I said the grad here, I didn't define it so well, right? So this is a grad here with respect to r. But if I do the grad with respect to r prime, I get rid of the minus. So that I'll write it down, and then this will be hopefully clear. What is the meaning of the grad now? And that's a good point. D tau. P, the macroscopic polarization field, dot grad prime. And the prime means that I'm doing the grad not with respect to r, but with respect to r prime, which means I'm switching this and then I'm getting rid of the minus. Of 1 over r minus r prime, yeah, d tau prime if you want. And again, this is an integration over the volume. And okay, now we could go home now, but of course, what do we see here? You see this is like this grad. So this is like this grad f here. And what is A? A is going to be the physical polarization field. So what I'm going to leave here is this part of the integral and of this expression, and I'm going to put this guy on the other side. What will happen? I'll have one term. I'll get rid of this grad. Why is that good? I'll repeat myself. Why is it good to get rid of the grad? When I get rid of the grad, I'll be staying with the Coulomb potential. So I want to get rid of this grad so it will act on the other things. But then the penalty I pay is from here I get 2 terms. What are these 2 terms? One of them is for the bulk and one of them is for the surface. This is how it comes about. So let us do this. Use bet. So V of r is equal to 1 over 4 pi epsilon. Integral over the volume over tau div. So again, F and A are these 2 objects. So div is P R prime R minus R prime d tau. So this comes from this guy. You see div, the multiplication of the functions. Here I multiply the functions. The div is with respect to R prime. Why do I like this? The div is with respect to R prime like the grad was with respect to R prime. This is a nice integral. It's an integral of a div. You can do the surface based on divergence, right? So this we will soon treat. But the second term comes from this term, and then what it means is that the grad was acting here. Now the grad is going to act on the P, but you need to use the div. So the other term is going to be, and you need to put it on the other side of the equation, so you'll get a minus integral over still the volume 1 over R minus R prime div rho of R prime. It's a vector, it's the macroscopic polarization field d tau. Okay, so now this one I know how to integrate. Okay, this is the divergence theorem I'm going to use. Again, to remind you, the divergence theorem just said if you have a div of some function, instead of integrating over the volume, you can integrate over the surface. I'm just going to use it, and then I'll get my answer. So V of R is equal to 1 over 4 pi epsilon integral over the surface. Surface of what? Of my body, whatever it is. So this is a two-dimensional integral. PR vector d tau, important R to the minus R prime to the power 1. That's the most important thing here. And
DA, no?
yeah, right. ds. Okay.
Dot.
Dot n. I already wrote it like that. This is dA. So n is a over here. There is a vector n. There is a vector n. ds is not is a scalar. ds n is dA. A vector, but now I'm already putting this dot because you see here, you see popping up. This is what I called before sigma b. So sigma b, of course, is not a vector, so it's a scalar. And then from the other term, I have this div b, which is minus integral now over the volume everywhere. Again, of the same surface, so this is d tau, div p. It's the div with respect to R prime. And here, let us emphasize this. R minus R prime. So I'm emphasizing that this is Coulomb-like. That's the whole point. And then I just need to close it. And this is what we called before rho of b. So I'm very happy. I proved what I said, right? This is the end of the proof. Now, you can say, but also these integrals are awful. And you're absolutely correct. Generally speaking, they are pretty bad. But you don't need these integrals in many cases. Why? Because this is the basic rule of electrostatics, given by charges and charge densities, and now you can apply everything that you want. You can apply Laplace, you can apply Poisson, you can apply Gauss surfaces, you can do whatever you want. Of course, all these methods will be useful and equivalent to the solution of this integral, but they will be useful when the problem is not difficult enough. That is fine, but all of electricity now, electrostatic holds with these replacements. All the toolkit that was developed up till now. So don't throw it to the trash. You still need to take it out of the trash and use it for solving real problems. So again, in a picture, what we have here is, again, we have this P, and we replace it by rho of B and sigma of B, and if you give me this function, I know these two functions, and then I can solve all kinds of interesting problems. So let us solve one example, so maybe you start getting a good feeling of this, or a better feeling. Let's say that the polarization is a constant inside the sphere. So I think about a ferroelectric. Again, a ferroelectric is simply many dipoles in the same direction, like a magnet, but made of electric dipoles. Or maybe they were created by some external field. I don't care. I don't care about the external field. Someone gave me this field, all uniform and all in a sphere. I don't care where it came from. And yeah, so we have a sphere, and we have P, and P is a constant, which means P is some P absolute value in the Z direction. So this is going to be the Z direction. And this is what is given inside this sphere. So, what can we say about this problem? First of all, what is the bounded charges?
0.
Obviously 0, because div P, even I can do that, is equal 0. And in the picture that we had before, what will happen here, you'll have here plus minus, plus minus, plus minus, and then plus minus. All these guys are cancelled out. And you are left with what? With some pluses on top. They are not evenly distributed. I'm not saying this is an easy problem, it's not. And some charges on the bottom. The total number of charges is the same. So we have this ferroelectric. So what is sigma B? That's what will create a problem which is not trivial. It's P dot N. Again, N is a unit into this direction. So if I put here in the middle of the sphere this angle theta, this is P dot N.
Exactly.
This is
theta from spherical coordinates.
yeah, the usual spherical coordinates. I even thought I don't need to say this, but this is the Z direction, and this is the N direction. The polarization is in this direction, the N is in the R direction, and this is by definition the cosine theta from the usual angular thing. So we have here, this is equal to the magnitude of this thing. That will depend on how many dipoles per unit volume we put actually inside there, multiplied by cosine theta. So you have here a very strange charge density that changes along this object. When you go theta equals 0, that it is maximum 1. So what happens here, based on this, you see the pluses. This is when theta is equal 0, it's a plus. When you're down here, theta is cosine theta is going to be minus. That's why you have a minus charge, as I already wrote. But okay, let's say here you have some charge density, here you have some charge density. What will happen in the middle?
0.
it will be 0, and the reason is physically you cannot really quickly go, and originally what you had here many dipoles, so in the middle there's nothing. So this is a very strange charge density, but physically now we understand where it comes from. We have here a ferroelectric material and all the dipoles are in this direction, or you applied an electric field and all the dipoles are in this direction, that's all. Now this problem you maybe solved already in electrostatics. I mean, I think you solved, maybe not, but okay, I'll remind you how to solve it. So first of all, what is the total charge?
0.
Yeah, it's obvious, but how do you see it? You just integrate over sigma b, and because cosine theta d cosine theta, this is how I integrate, is equal to 0, total charge is 0. These are just sanity checks. Total charge is 0. We understand the physics, and now we understand why. Maybe someone asked you this question previously with a very strange, you thought he was a mean person. And okay, how do you solve this? This is going to be a reminder. Or I'll just give you the solution, and then we can, I'll explain how to derive this, but first let's see what is the solution.
The solution to what? To the potential, or?
Yeah, what is the potential? So how do we solve this? I mean, you should know how to solve this problem. I told you already, this is just electrostatics. How do you solve these problems? I mean, maybe there are many ways, but you have now a sphere with sigma b on inside. What is the Laplacian of the potential inside? 0, because there's no charge inside. So
Yeah, 0.
we just have this sphere, and here rho v is 0, and here Laplacian v is 0, and on the surface there's charge. What does it mean? That there will be a jump in what? In the electric field. The potential field will be continuous. So you solve you solve Laplace equation inside, you solve it inside, and you match with the boundary condition. I'll soon do that to remind you, but this is something that we taught. It's not from high school. Okay, now we are at lesson number 4, so now the joke will shift. You learned it from high school to you learned it at 2 weeks ago. Okay, whatever. Oh, you learned it at Jonathan Rochman's course. Okay. So, okay, so what is the potential? I'm not solving, I'm just giving the answer now. Obviously it does not depend on phi, on the angle like coming out of the wall, because also the potential just from symmetry. So VR theta is equal to the following: P R cosine theta. The cosine theta comes essentially from here. 3 epsilon 0, and this is for R less inside the ball. Then outside the ball it is P R to the power 3 cosine theta 3 epsilon 0 R to the power 2. This is R bigger than R. So the field, both inside and outside, depends on the coordinate r. It's not a constant. The polarization is a constant, but the field itself is not a constant. Okay, so what does it tell you? Let's look what happens inside. What is r cosine theta here? That's simply z, right? So what is happening here, there's a polarization in the z direction. So there's a symmetry breaking in the z direction. So this is z. Why is it better to write here z? If this is z, this is the potential. What is the electric field inside? Yeah, what is it? You just need to take the derivative, and you need to use not the spherical coordinates. It's just the derivative with respect to z. That's with the minus sign. That's the electric field inside, according to this formula, and that means that the electric field is simply minus p over this 3 epsilon 0 inside. So the electric field is simply d v z with a minus sign. That's E, and it's like that inside. And its magnitude is the polarization. If the polarization is 0, obviously you have nothing, and that's it. It's a constant field. What is it outside? What is this potential that is written here in a strange way? You have 1 over r up to the power 2. What is it? Not Coulomb. It's a dipole. This is not so surprising. We started with a macroscopical dipole. Everything is up here, and then outside we get the 1 over r to the power 2. The cosine theta was also effectively in the dipole. So this coefficient here, what is it? It's the effective dipole of all the system. What do I mean by all the system? With the sigma b. So we can think about all this system with the p as an effective dipole, and outside it's acting like a dipole. This is what this equation says, but it says a little bit more, because this is the dependence on r and cosine. It's like the dipole potential, but now we know what is the dipole strength. Again, the effective dipole strength outside. So what is it? I mean, exactly. So let us just remember, compare this one with the equation we had before. I mean, V dipole, it was like this. P, the small p, if you remember, dot r 4 pi epsilon. And of course, we had here the power 2. Oops. So you see the 2 here and the 2 here, and this when you think about it a little bit will translate into this cosine theta. How exactly? What is the effective p? This no, it's not an integral. It's something very simple. It is 4 pi r to the power 3 over 3. This is the volume of the sphere, multiplied by capital P. And this is not the definition. This is what I see from this equation. Because if I put this definition in here, you see the 4 pi will cancel with this. The 3 is this 3 with this epsilon. So this is just the meaning. So this describes, it's both the potential of a dipole, but it just describes this thing. These two things are exactly the same. So we got what we expected. This is the polarization density multiplied by the volume, gives you the effective charge, which is a macroscopical charge, macroscopical dipole. This is not a single particle dipole anymore. Okay, I think this is clear. So if I add now, how does the field look like? So again, inside it looks like this. And then outside it looks like this. This is the famous picture, which I'm very bad at, so ask chat to do it. It does it much better than me. I'm actually surprised so many students are in the class. The next students will not come to class. So this what I try to plot is this is simply the field of the dipole, and what you see up here is the positive, and then the field goes up here, but from here it goes down because this is the negative. This is the effect on a positive charge, so the field lines go up here and down here, and of course when the density is less and less, the strength is less and less. This is related to this turning here. So this is our field, and we also have the picture of the dipole electric field, and this is this problem. Now the question is, should I explain how to get this, or do you want me to explain this? I didn't say. I said this is the answer. Do you want me to explain it or not?
No.
Just the Laplace?
Yes or no? I don't hear you.
No.
No. You? No, yes? Okay. So, but this is given, again, you separate the two regimes and you use the usual trick of separation. You can solve this if you want. Okay, so it's important that you know how to solve this. I mean, I assume you do. What is the time now? Okay, so let us move on a little bit more. Now we want to okay, I think maybe we'll stop now because sometimes I took more time from you and now your lawyers came to me and said, why do you teach us so much? So now I'll give you back what you deserve. And I don't want to start something new. Maybe you're also tired. So let us stop here and we will, I hope you don't mind. It's a joke. Okay, so we will end here and then we will continue the dielectric medium. Please read chapter 4 in Griffiths. Here, unlike the green functions and all kinds of things I did previously, I'm following Griffiths. So here Griffiths is really good in my opinion, and I like to stick to him first of all because in my opinion this material is not so trivial, because what is a dipole polarization field? You need to think about them very carefully. And the beauty of it is that this is old physics, and old physics is real physics. So you should enjoy Griffiths as much as you can. So let us meet next week, and I might add on Monday, I apologize, a lesson at 8 in the morning. The reason is I'm maybe leaving if there's no war. So I need to adjust in advance. Okay, thank you very much and have a nice weekend.
Thanks a lot.
מעין פה. מעין פה הוא באף.
כן, לכן